Hi everybody, this video is about the sum of geometric series. And I don't mean the sum of a finite number of terms, I mean an infinite number of terms. And it's kind of an astounding fact that you could add an infinite number of things and the sum doesn't just balloon out to infinity, but actually approaches a particular finite value. Series for which that occurs are called convergent series. So if your infinite sum is approaching a finite value, that's called convergent. If that's not happening, your sum is called divergent. So let's start with this geometric series. Why does that converge? How do we know it converges? It seems intuitive that maybe it might, but how do we know? And what is it converging to? So the most direct way of showing that any series at all converges would be to look at the pattern that's formed when you add more and more terms. And we call these partial sums. And you designate them with little subscripts. So if this infinite series is denoted S, S subscript 1 would be the first term, S sub 2 would just be the sum of the first two, S sub 3 would be the sum of the first three, and so on. So if we want to know, does this infinite series converge, what we really want to know is what's happening as we add more and more terms. So we're going to look at this sequence. So if we were going to actually write down these numbers, I probably should have done this, you'd see that so this is like 1, this is like 1.5, this is like 1.75. So you see that the sums are going up, right? Every time we add a new term, the overall total is increasing, but it's increasing by a smaller and smaller and smaller amount. So that leads us to believe that maybe this isn't approaching infinity. Maybe the more and more terms we add, this is going to start approaching something particular. So how could we decide what that was? The easiest way to do that is to come up with an equation for the nth partial sum. So what's an equation for the sum of the first n terms? And then look at, well, what does that equation look like when n approaches infinity? So let me just remind you how we did this the other day. So this is the equation for a general geometric series. We've got a number, and then each successive term, we're multiplying it by r, which is our constant ratio. So if I wanted to derive an equation for what is this summation equal to, the way we did it was we started by writing the sum, then we start by writing the sum again, only we're going to multiply both sides by r. So if I multiply the right-hand side by r, that's the same thing as if I multiply each individual term by r. And then you subtract the two. So here I've got Sn minus r times Sn. On the right-hand side, I've got a, and then I've got ar minus ar, so those cancel. Ar squared minus ar squared, so those cancel. And everything cancels all the way down to this last term. So I've really got a minus ar to the n, and now I can pull out that s subscript n, which is the thing that I'm trying to solve for. Remember, that's the sum that I want. And so now I can divide through by 1 over r. So a minus ar to the n over 1 minus r. So there's our general equation. So let's see how we can use that back in the original problem, which is where? Here it is. All right. So we just decided that the nth partial sum equals a minus ar to the n over 1 minus r. In our particular scenario, let's see, a is the first term, so that should be 1. R is the thing we're multiplying by to get from one term to the next, so r is 1/2. So for us, we've got that the nth partial sum here, the very bottom, equals 1 minus 1 times 1/2 to the n divided by 1 minus 1/2 is just 1/2. All right. Whoop. So it's all on the screen at once, sort of. So the question is, as n gets really large, what's happening to this equation? Well, let's just look at, well, you'll notice that this isn't changing and that's not changing as n gets larger. It's only this part that is. So what is this part approaching as n gets really large? And you might think, well, whenever I have anything that's smaller than 1, if I multiply that by itself over and over and over again, that product is getting smaller and smaller and smaller. 1/4 is smaller than 1/2, 1/8 is smaller than 1/4. So this part of the equation seems like it's going to approach 0. So our question is, what's happening as n is approaching infinity for this partial sum? And the intuitive answer seems to be that this part is approaching 0, so I'm left over with 1 divided by 1/2, which is the same thing as 2. So what that's telling me is that my original infinite series seems like it's approaching the value 2. And I did that by looking at the sequence of partial sums. All right, let's do that same thing in general, and then I'll have an even more general point to make. So in general, if we've got a geometric series, if we've got a series that's AR squared, blah, up to AR to the n, and then onwards. So that's our full geometric series. We know that the equation for the sum of the first n terms is A minus A times R to the n over 1 minus R. And so if our question is, what does this converge to? That's the same as asking, what's happening to this equation that tells us the sum as the number of terms approaches infinity? So we want to know limit n approaches infinity of this nth partial sum. What's that equal to? So as we saw, well, all right, so hold on. Let's imagine that A equals 1 and R equals 2. In that case, we've got the sum 1 plus 2 plus 4 plus 8 plus 16. So clearly this sum is not approaching a value. This sum is getting larger and larger without bound. So this is not a convergent series. This is a divergent series. So it seems like at a very minimum, if you're going to add up an infinite number of things and have that sum approach a finite value, the things that you're adding have to be getting smaller and smaller and smaller. And it seems like the things that we're adding are only going to get smaller if what we're multiplying by to get from one term to the next is smaller than 1. So let's impose the condition that absolute value R is less than 1. Why absolute value? Let's think about that in a minute. But let's say R is less than 1. So in that case, just like in our other example, this part is going to approach 0 because we've got something whose magnitude is smaller than 1 being multiplied by itself more and more and more times. So that's going to approach 0. So if that's really true, then we've got that this entire limit is going to approach, or is going to be equal to, A over 1 minus R. And this is, in fact, the equation for the sum of an infinite geometric series. This is only true for series that are geometric, because the way that we got this was by figuring out what's the nth partial sum, and then looking at what happens to that as you approach infinity. What about series that are not geometric? So in that case, you can still try and do the same thing. Well, here, let's look at this one. So here I've got 1 plus 1/2 plus 1/3 plus 1/4. If I wanted to try and show that this converges, because my intuition says maybe it does. You know, each term is getting smaller, approaching 0. So that's a situation where as I'm adding more terms, yes, my sum is getting larger, but it's getting larger by a smaller and smaller amount. So if I wanted to try and show that that converges, the approach that I might take would be, let's try and come up with an equation that will tell me what is the nth partial sum, and then look at what happens to that equation as n approaches infinity. So that's something that you could try. In general, it's pretty hard to come up with an equation for the nth partial sum. There are a lot of sums where that equation is not really going to be a feasible approach to solving it. So in calculus, you're going to learn a ton of other approaches that you can use for trying to figure this out that use the couple of sums that we do know to try and let you conclude things about sums that we don't know. So like a really easy example of this would be, what happens, all right, so let's do this. What happens if I've got a sum whose nth term is 1 over 2 to the n times the natural log of n times the square root of n plus 1. So that seems kind of messy. And it seems like it's not going to be that easy to figure out. What's an equation for the sum of the first n of these terms. But something that I'm noticing is as long as this part is larger than 1, each of my terms, with this ugly stuff, each of my terms is going to be strictly smaller than the geometric series that's formed by 1 over 2 to the n. And the geometric series is the one that we just looked at. So if I have an infinite sum where every single term is smaller than another infinite sum that I know converges, then I can conclude that my infinite sum also converges. If that made sense, awesome. If that didn't make sense, don't worry so much about it. That was a pretty quick summary explanation. But that's an example of a kind of a test that you would run in calculus. All right, maybe that's enough. Maybe that's more than enough for the moment. If you're curious about that thing I just said because it didn't make sense and you want another video that explains it a little bit more fully, I can do that. For the moment, that is all.